All right, today we're tackling a real mathematical monster. One of those problems that, for centuries, everyone just agreed was, well, impossible to solve. But what if they were wrong? What if impossible was just waiting for the right key? Just look at this thing. An 18th degree polynomial. I mean, where would you even start with that? For centuries, the best answer math could give us for something this complicated was basically a guess. A really, really good guess, sure, but still just an approximation. So here's how we're going to break this down. First, we'll dig into why this kind of problem was considered impossible in the first place. Then we'll see why the old ways of solving it just fall short. After that, we'll introduce this revolutionary new theorem, and you'll see how it takes us from this crazy complexity to something shockingly simple. And we'll wrap up with why getting an exact answer is such a huge deal. All right, so let's get into it. What makes an equation like this so tough to crack? Well, it really boils down to the limits of the tools we've had in our mathematical toolbox for, forever. You can think of it like this. The old methods, the classical ways of doing things, are kind of like trying to hit a bullseye by just throwing a bunch of darts at the board. You'll get close, right? Maybe even really close, but there's always going to be some error. This new theorem, though, it's like a single arrow, perfectly aimed, that hits the dead center. Every single time. That's the difference we're talking about. The difference between close enough and perfectly exact. And, making a claim like that it's a huge deal. I mean, for almost 200 years, a cornerstone of math has been Abel's impossibility theorem. It basically says that for equations this gnarly, finding a nice, clean, exact formula is, well, impossible. And this new theorem just waltzes in and says, actually, about that. So, what is this game-changing new tool? Well, it's time to introduce the star of the show, Euclides' theorem. Okay, deep breath. At the core of this whole thing is this recursive formula. And I get it, it looks intense, a whole mess of symbols and letters. But don't panic, we are not going to work through the math here. What's really important, the thing to focus on, is what this formula does. Because what it does is actually incredibly simple and, well, elegant. The best way to think about this formula is like a refinement machine. It grabs a piece of the original super messy equation, chews on it for a second, and spits out a much cleaner version. Then it takes that cleaner piece and runs it through the machine again and again, getting simpler and simpler each time. It's this beautiful loop that just boils all that complexity down to its absolute core. Okay, so here's the big question, right? What happens when we actually let this refinement machine loose on our monster polynomial? Well, this is where things get really, really cool. The theorem gets to work. It runs its little loop 18 times, and out pops a totally new set of 18 coefficients. And these new numbers, these R's values, they are the secret key that's going to unlock this whole thing. And this is where you can really see the power of this theorem. Just look at these new coefficients it created. The first 8, all 0, gone. Coefficients 9 through 16, also 0, vanished. All of that insane complexity from the original equation, all those different terms, they've just been systematically wiped out. We're left with just 2 numbers that aren't 0. The complexity is just gone. And this amazing simplification brings us right to the big payoff. This is the aha moment we've been building towards. So that monster equation we started with, the one with 18 different parts, it's been completely transformed. It collapses down into this beautiful, simple, 3-term equation. And this is something we can finally work with. This is solvable. And from that super simple equation, we get this, the exact roots. And let me be clear, this is not some long decimal number you get from a calculator that you have to round somewhere. No. This is the actual answer, written out perfectly. It's precise. It's what we call a symbolic solution. It's mathematical certainty. Okay, so that's awesome, right? We solved one ridiculously hard math problem. But, so what? Why should anyone outside of a university math department care about this? Because this is so much bigger than just one equation. This points to a fundamental shift, moving away from a world of close enough to a world of exactly right. Think about fields like, say, quantum physics or high-level engineering. In those areas, tiny little rounding errors can build up and lead to huge mistakes down the line. A method that gets rid of those errors completely isn't just a minor upgrade, it could be a whole new foundation to build on. It's a way to find perfect answers where we've always had to settle for good enough.
And that really leaves us with a pretty mind-bending question to chew on, doesn't it? If a problem that mathematicians literally called impossible for hundreds of years can suddenly be solved with perfect accuracy, what other unsolvable problems are out there right now just waiting for someone to come along with a new way of looking at them?